Hello, everybody. I've agreed to talk on, as you see, a brief introduction to the hydrology of peatlands, and maybe some of you will know me, probably some of you won't. So here's a very brief biography, just to prove that I'm not a complete charlatan talking about this. I suppose the main things are that I've got a doctorate in hydrogeology, and I've been working on peatlands and peatland eco-hydrology since about 2006, so about 15 years. And it's interesting that hydrogeology, wetland and peatland hydrology is basically hydrogeology or groundwater hydrology in miniature. So I think a lot of the things that I was working on at a large scale when I was working on groundwater resource hydrogeology are just miniaturized quite often in wetland hydrology and peatland hydrology. So I found that it's quite a fertile ground to apply hydrogeological expertise. And I worked for a company that I founded in 2008 called Recolonization, which means it's based on Latin for irrigation. So what we're going to look at today, I thought that we'd quickly look at water and peatlands and why they're fundamentally linked together. Why are peatlands wet? Interesting question. And how humans have managed to mess up peatland hydrology in many and varied ways. And then how we're trying to fix the mess that humans have made and are making to peatland hydrology, to try and get peatlands working for us again and providing the ecosystem services in the current trendy terminology. Now here, I wasn't sure about the scientific knowledge of the audience, so I've tried to make this as accessible as possible. So there are some simplifications, and this is just a note to say that if you think you've spotted any or you want to discuss any at the end, or indeed afterwards by email or give me a ring or whatever, or that's the one plug that there's going to be throughout the whole lecture, is you can come to one of my courses that I give on Introduction to Wetland Hydrology. So that's the plug over with. So water and peatlands, I'd say that they were fundamentally linked, and so here we are, we're in lockdown and we're thinking, oh goodness, what can I do? What am I dreaming about doing in lockdown? And then you think to yourself, oh, I could go and visit that really nice raised bog or that really nice blanket bog that I went to a few times before. I'm really dreaming of going back there again. And the next thought you're going to have is, where are my wellies, nationalist wellies or otherwise? And that just at a very basic level tells us that that water and wetness and peatlands are fundamentally and I think correctly linked in our minds. So why is water important for peatlands? So at the top left there, we've got a nice beach woodland, and at the top right, we've got a peatland section. So there's some peat turfs there at the top, which have been cut for burning. And I would say that section there is probably about 2 meters sequence of peat. So the fundamental importance of water to wetlands is through the fact that anaerobic decomposition of vegetation litter is much faster than anaerobic decomposition of vegetation litter. And we know that the rate of oxygen diffusion is 10,000 times less in water than it is in air. So when we get in a natural peatland, if we've got permanently saturated conditions, that is going to promote the dominance of anaerobic decomposition over aerobic decomposition. Because once the rainfall lands on the peatland, and the natural processes quickly exhaust the oxygen, the dissolved oxygen in the water. And then the only oxygen that you can get for decomposition is through diffusion of oxygen from the water surface or the water table. As you can see, if oxygen diffusion in water is 10,000 times less in water than it is in air, that the flow of oxygen through diffusion into the saturated zone is going to be very slow, and you're not going to get much aerobic decomposition. So anaerobic decomposition dominates. And that means that in peatlands, by definition, because we've got accumulation of peat, that allows an excess of litter addition over decomposition. So if you've got more litter, more vegetation litter, so dead vegetation falling to the floor or in situ, you've got more addition of dead vegetation than you have of decomposition. And from a mass balance point of view, you're going to get an accumulation of organic matter. And that accumulation of organic matter is peat accumulation. So in the top here, we've got our beech woodland, and we know that if we went to this beech woodland with an auger, we'd auger down, and we'd maybe find 20 centimetres of woodland soils, maybe organic rich woodland soils, but then we'd get down into inorganic soils, and that would demonstrate to us that aerobic decomposition was dominant, and that aerobic decomposition was generally higher than the amount of leaf litter coming down and other litter coming down from the canopy. So you don't get a build-up of organic matter in this beech woodland. Whereas in the peat case, you've got this dominance of anaerobic decomposition because you've got very high water tables, so you get an accumulation of peat. So that's the main reason why saturated conditions are really, absolutely vital for the accumulation of peat. So there we are. Permanently saturated conditions are a fundamental condition for the existence of peat, and that includes the initiation of peat formation, the accumulation of peat through time, so during the Holocene, since sort of 10, 11,000 years ago, and also the stable existence of peat. So we think one of the ecosystem services that we're particularly concerned about at the minute is the storage of carbon in peatlands, and saturated conditions are absolutely vital for that stable storage of carbon within peatlands, so that carbon isn't released into the atmosphere as either methane or carbon dioxide. So we're really looking for saturated conditions in peatlands that we're restoring, and we know we've got saturated conditions in natural peatlands to the degree that we can identify natural peatlands in the UK. So back to the list of what we're going to look at, and so we'll go on to why are peatlands wet. So I'm going to introduce what I'm going to call a thinking framework for peatland hydrology here. So it's a very simple. If people have done my course or one of my courses, you'll know that this is introduced as a very simple conceptual model. But I'm going to call it a thinking framework here because that's a little bit more accessible. So when we're thinking about peatland hydrology, we can think about three functional elements. So we've got, first thing is water supply. Where is our water going to come from into our system, into our peatland system? And we've got Rainfall is often very dominant in peatlands, especially, I'm not going to go into we can go into later the differentiation between, or the terminology of peatlands between fens, bogs and mires, etc. And that's where some of these differentiations come in. But I'm just going to say for the minute that rainfall is quite important as a water supply in most mires. We've also got surface runoff. So when we get generally when we get high rainfall events or high intensity rainfall events, we get surface runoff. So that's when we get runoff and we get excess rainfall. We don't get infiltration into the soil, and some of it runs off across the ground. We've got groundwater inflows. So those are the main three water supply mechanisms to mires, peatlands, and possibly surface water. So if we get surface water flooding, that's specifically for fens, which we can go into later on. So those are the four basic mechanisms or possible mechanisms of water supply to peatlands. And then we've got water retention. Now this is this is where it gets a little bit more conceptual. Water retention is a property of the peatland itself. So I'm just, rather than putting arrows up, which makes it a little bit easier to sort of conceptualize in your head, what I'm forced to do here is just put a little ring around our peatland and say the water retention features are a feature of the peatland, or the water retention capacity is a feature of the peatland. And we'll go on to have a look at this in a second. And the third one, you might have guessed this, is water loss. Now, you'll notice that water loss there is in brackets. This is more difficult to talk about conceptually, and to a certain extent, it links up with water retention within a peatland. And I've put it in brackets there because I'm not going to talk about it very much, if at all, during this talk. So, but just for completeness, we can see that we've got, these are the mechanisms of transpiration from the peatland surface. We've got possible groundwater flow out of the base of the peatland, and I can give you a specific example of that later on if anybody's interested. And we've got outwards flow into surface water courses, streams or rivers. So in general, apart from very specific examples, the main water loss mechanisms for peatlands that we're worried about are going to be evapotranspiration. And just to say, evapotranspiration is a word which is a combination of evaporation. So that would be evaporation from free water surfaces, so free water in pools or what have you sitting on the top of the peatland, and also transpiration, so transpiration water loss directly through plants. So as hydrologists, we maybe concatenate is the word, I don't know. So we put those words together and we come up with this term called evapotranspiration, or often termed EVT. You'll see that in diagrams in the literature. So the main water loss is evapotranspiration and surface water flow, so seepage through the peat and into surface water courses. So that's our sort of thinking framework, a very simplistic thinking framework for how our peatland is going to work. So remember, we're thinking about why peatlands are wet here. Now, I don't know whether you can see these very well, but these are maps that I lifted off the internet yesterday. So the left-hand side one is, and we don't need to worry about the detail with this, but the left-hand side one is a map which shows the distribution of peat, and I think the variable that's used, the actual variable used here, is the mass of carbon per metre squared. as an effective surrogate for depth and density of peat. So we don't need to worry about that too much. We just need to look at the general distribution. Oh, that's my mouse. Yeah, I don't know if you can see that, but we can see that, I mean, basically, all of the peat, or kind of, 90–95% of the peat occurs in the northwest half of the British Isles. And if we look at the central map here, is the rainfall distribution. And we don't need to go into details, but we can, surprise, surprise, we've all got a good idea of what the rainfall distribution is in the UK. And we can see that the rainfall distribution has got very similar spatial distribution, spatial variation in terms of the rainfall distribution to the distribution of peat. And then if we look on the right-hand side map, we've got average mean temperatures in the British Isles. And once again, you can see that, sorry, I might have to go and shut the window in a minute outside. You can see that, and this isn't a surprise, we all kind of know this, we can see that the temperature distribution, we've got generally colder conditions in the north and the west, and warmer conditions in the south and the east. And I'm using this, the relationship is a bit more complex than this, but I'm using this as temperature as a surrogate for evaporation. So you can see from those three maps, you can see the peat distribution there, you can see the rainfall distribution there, and you can see the temperature or the evaporation distribution there. And you can see that both of these, both the rainfall and the temperature distribution, are very similar to the distribution of peat, or are related closely to the distribution of peat. So one of the things that we talk about in hydrology is a term called effective rainfall, and this translates, or it's a very useful concept in peatland hydrology as well. An effective rainfall is basically rainfall minus evaporation. An effective rainfall is that you can see here that if you subtract the amount of evaporation that you're likely to get according to that distribution from the rainfall distribution, then the effective rainfall distribution is going to be very similar to this distribution, but it's going to be even more marked, with high rates, high levels of effective rainfall in this part, the northwestern part of the UK, and that will map really effectively and really closely onto the distribution of peat within the UK. So this is a photo of Richard Lindsay. It's a little bit of a scary photo of Richard Lindsay, actually, given the projection. But here you can see one of his points in putting this photo on the internet was that peatlands are generally wet. So the spatial correlation between the occurrence of peatlands, higher rainfall and lower temperatures, we saw that in the last slide. So higher effective rainfall, you tend to get peatlands. And I think it's safe to say, I mean, that's just a correlation, a spatial correlation that we're seeing. But I think, given what we've seen before and what we'll look at afterwards, after now, we can infer some kind of causal relationship between those variables that we look at. And if you look in, there's various examples of this. John Rodwell, I think, is in part his notes is the notes on M18 vegetation, which NVC M18 raised bog vegetation, and he suggests that that's only found where rainfall is between 800 and 1200 millimetres per year, and where there are 140 to 180 rain days per year. So that's actually a concrete example in the literature of where people are saying that the spatial distribution of meteorological variables, specifically the effective rainfall, is very closely related to the distribution of peat. So now if we go on to, so that's just a little bit about the water supply aspects of our thinking model for peatland function. And now if we go on to peatland water retention. So I thought I'll go online. Almost gave the game away there. I went online and I just Googled peatlands and then clicked on images, and this is what came up. So and you can this is where it's quite difficult, because at this point I'd ask you all what was the common property of all of these peatlands that you're seeing in the Google search when it comes up, and so you've got a little bit of chance to have a look at that, and I'll suggest that the common feature of all those peatlands is that they're flat. So peatlands generally tend to be flat. And the effect of them being flat is that water runs off, so you get surface runoff peatlands, and you get seepage within the peat. And both of those processes happen more slowly because the peatlands are flat. And that means that the water is resident for longer on peatlands. And the fact that the water is resident on the peatland for longer means that you've got a higher water table generally, and you've got greater saturation. So that feeds back into our, you've got higher water tables, you get anaerobic decomposition, and it favours the accumulation and stability of peat. So peatlands are flat, and that helps to explain why they're always wet, or why they're generally wet. And we've got here, this is information from the Habitat Survey of Wales, and I think it's for mainly blanket bog. So this is vegetation survey for Wales, and it's quadrats of blanket bog. And the surveyors took the slope of the quadrat, or the slope surrounding the quadrat of blanket bog. And I'm not sure whether you can see the numbers up the side. So this is a cumulative frequency curve. So on the y-axis, you've got cumulative frequency running from 0 up to 100, or 105 for some reason, but we'll gloss over that. So up to 100 on the y-axis. And then we've got the slope angle on the x-axis. And you can see that, well, about 85% of blanket bog peatlands, and this actually doesn't take account of the depth of peat. So where you've got any kind of blanket bog vegetation, 85% of the occurrence of blanket bog vegetation is on ground where the slope is 10 degrees or lower. So that's some actual empirical evidence, apart from the photographs that we saw on Google, that the flat ground favours peat accumulation. So that's quite a nice bit of evidence to back that up. So the next aspect of water retention in peatlands that I'm going to talk about is a little bit more complex. And I'm going to start by presenting you with this, which is basically a pile of gravel. So if you can imagine, in a builder's yard, you've got a large pile of gravel in a builder's yard, and you've got a certain amount of rainfall coming down onto that pile of gravel. Now, if we put some monitoring into this pile of gravel, we might find, or we probably would find, this blue line here is what we call the water table. So, and if we put some monitoring into the pile of gravel, we would find that the water table was quite low relative to the surface of the pile of gravel. So the water table is going to be very low within the pile of gravel. And you know, hopefully you can imagine this. You wouldn't expect, if you had a pile of gravel in your backyard, you wouldn't expect it to be holding much water. So, you know, the water table within that pile of gravel is going to be quite low and quite close to the ground or quite close to the concrete in your backyard. And the reason for that is that the hydraulic conductivity or the permeability of that pile of gravel is very high. And because the permeability is quite high, it facilitates, well, firstly, flow of water down through the gravel. And then more importantly, it facilitates lateral flow below the water table out to the sides. So what you would see during a rainstorm is that you would get quite a lot of water discharging at the sides of the pile of gravel. And overall, the amount of storage in the pile of gravel would be very low, and your water table, by definition, would sit quite low in the pile of gravel. So that's the sort of first example. And the key aspect of that is that the hydraulic conductivity or the permeability of the gravel is quite high. So contrast that with this pile of peat, which you can also call, or you can also imagine, is a raised bog. So we've got the same amount of rainfall coming down onto the raised bog, but we see that, and hopefully you can see that our water table is very close. I'm just tracing that with my mouse there in case you can't see it. So we can see that the water table is very close to the surface of the peatland. And the reason for that is that the hydraulic conductivity or the permeability of the peat is relatively low. So when the rainfall falls onto the peat surface, the peat becomes saturated, and because the hydraulic conductivity is low, and we know that anything below the water table is saturated, the hydraulic conductivity or permeability of the peat is low, so it provides resistance to flow out from the centre of the bog to the outside of the bog. So relative to this pile of gravel that we've got here, we would see relatively little water coming out at the sides of the bog, and we would perhaps see more water running over the surface of the bog, so surface runoff rather than groundwater flow through the peat. And that demonstrates a key aspect of peatland hydrology, in that the property of the peat being having a low hydraulic conductivity or permeability, we say as well, means that it resists water flowing away, resists groundwater seepage within the peat, and therefore it helps to retain the water table close to the surface of the peatland. So here we've got this guy's called Professor Andy Baird, and this is him doing some hydraulic testing of wells, and he's actually measuring there. This was in Panama. We went to some tropical coastal peatlands in Panama. And Andy here is doing a test to measure the hydraulic conductivity or the permeability of the peat in this peatland. So peat has a relatively low permeability, and that provides the resistance to water loss by seepage from peatlands. And it's important. And so I would say that the low permeability of peat is actually an existential property of peat, because in most cases, if if the peat wasn't poorly permeable, it by definition it couldn't exist. Because when you get peat accumulation, if the water table doesn't stay close to the surface of the peatland, then aerobic decomposition takes over, so you can't get accumulation of peat. So this low permeability of peat is actually an existential property of peat. And if we do these kind of hydraulic tests that Andy's doing here, we can show that the permeability of peat is generally similar to that of silt or clay. So some of you might have dug a garden pond and lined it with clay. And the reason that you line it with clay is that clay has got a low permeability, a low hydraulic conductivity. Well, when you do hydraulic testing of peat, in most cases you find that the peat can have equivalently low hydraulic conductivity to silt or clay. So that gives you some idea of the hydraulic properties of peat. So that's why peatlands are wet. This is snuck in here because I forgot to delete it, but we can have a look at how you monitor and understand peatland hydrology a bit later if we've got some time. So we'll go on to how humans have messed up peatland hydrology. And I'm going to quickly look at climate change, peatland drainage, and this is just etc. down here to acknowledge that humans have found many and various ways of messing up peatlands, but we've only probably really got time to have a look at a couple of them. So if you go on to, there's a nice link for you there, depending on wherever you live in the UK, you can go on to climate projections, and UK climate projections gives you information from a suite of climate change global circulation models, which tells you on various time horizons what the climate is projected to do in your location, depending on the best scientific knowledge as expressed through global circulation models, global climate models. So in this particular piece, I took some projections off this website for a course that I gave in Monmouth. So this is for my local area. So it's for 25 kilometres square, which includes Monmouth and Abergavenny. There are summer predictions, so for June, July and August. And the time horizon here is for the 2050s. And the changes, the anomalies or the changes that this is predicting is based on the 1961 to 1990 baseline. So we're going to see percentage changes in various variables, and those percentage changes are based on that baseline from 1961 to 1990. And you can look at various emission scenarios. So unfortunately, apart from the last 2 months, where there's not been that much, or there's been much fewer emissions going up into the air because of obvious reasons. Before the last 2 months, we were actually running along the high emissions scenario, but these predictions that we're going to see in a minute refer to the medium emissions scenario. So this is for all those details that I gave in the last slide. This is taken from the UK projections website, and this is the percentage change in rainfall. So so the central estimate there, and this is for the summer, the central estimate is minus 20% of rainfall. And so you've got a statistical distribution which reflects the uncertainty in the climate models. But you can see that if you take there are 5% chance either side of that distribution. You've got minus 60% rainfall or plus 35%. But the central estimate there is minus 20% of rainfall. And this is 2050. And then if you look at, so we're concentrating on those variables that we looked at the maps for earlier in the presentation. So if you look at the change in temperature for the same details that I looked at, that I told you about just now, the central estimate there for the summer in the 2050s is average temperatures will be plus 1.8 degrees C, so more or less 2 degrees C higher. So we've got minus 20% rainfall, and we've got plus 2 degrees C in temperature during the summer. And either side of that distribution, we've got minus 1 degree C or plus 5 degrees C. But our central estimate is that plus 2 degrees C. So looking, you can see that, you know, thinking back to what we looked at before, we said that the effective rainfall is a really important variable in terms of determining where peatlands are going to occur and where, you know, where favourable conditions are likely to occur for peatlands. And we defined a southwest to northeast line through the UK, to the northwest of which it was likely that, you know, favourable conditions for peatlands would occur, and to the southeast of which favourable conditions were unlikely to occur. And you can see, I mean, those figures that we've just looked at were based on Abergavenny, but if you looked over the entire country, you wouldn't come up with vastly different projections for the climate. So we can see there that given those changes to the climate, that line which is going to define the boundary between generally unfavourable and favourable conditions for peatlands is going to quite rapidly move northwest, which is going to mean that, you know, you're going to reduce within the UK, you're going to reduce the amount of ground where favourable conditions for peat accumulation and peat storage are likely to occur. So where the line moves from its current position to its future position, you've got a lot of peatlands within those two lines, which potentially, you know, fundamentally in meteorological terms, you're not going to have favourable conditions for the stability and long-term existence of that peatland. So the translation of those predicted changes onto peatland hydrology is a bit more challenging than what we've just been talking about. But, you know, generally that what I've just said is a reasonable summary of that. And it's, as I say, that it's clear that there will be effects on the distribution of peatlands and the condition of peatlands within the UK as a result of climate change. So I just said that the line marking those peat favourable hydrology will move northwest. And I think it's important for, you know, hopefully there's a few site managers and people who are in charge of sites, so we've got influence over sites listening at the minute, watching. So those projected changes are for the 2050s. And that should be, if we're investing a lot of money into peatland restoration in 2020, or, you know, over the next 5 years, 2020 to 2025, peatland restoration is quite an important activity in our community. But I'd argue that those projected changes are only for the 2050s. So that 2050 should be within our management horizon for peatlands. So we should be thinking, I'm going to invest X million pounds here in peatland restoration. But if I look at the projected changes, and if I get some peatland hydrologists to work through the projected changes in climate, is the peatland that I'm going to be doing this work on and spending X million pounds on to restore it, fundamentally, is it going to be sustained over the long term and certainly till the 2050s? It might be that the meteorological conditions mean that it's not sustainable in the relatively near future. So, you know, should you be investing that money where you're investing it, or should you be looking to invest it somewhere else? And I'm not saying, I'm not giving any examples here, and it's just a kind of generic thing. I think we need to be thinking about that. And you know, it's very difficult to project climate change, or to say that any particular weather event that you're seeing is a result of climate change. So I'll put that caveat down before I say this. But I was on site for the first time in 2 months at Borth Bog on Monday, and I met Justin Lyons, the site manager, and he said that he was going to go on site in walking boots. And I've never bogged in walking boots. And I just thought, well, fine, he's been on quite a lot lately. I spent the whole day on Borth Bog just in walking boots, and I didn't get wet feet once. And normally it's absolutely you need to wellies, and quite frequently your wellies go. Quite frequently you go over your wellies in Borth Bog. But at the minute, I mean, it's raining outside here, so it might be a bit better today. But on Monday, after 2 months of relatively little rainfall, Borth Bog was effectively dry on the surface. So, you know, whilst we can't, as I say, we can't directly map weather events onto climate change. You know, we're getting the idea that things are changing. So that's climate change. I've got no means of knowing what the time is, I don't think. Anyway, I'm sure Katie or Becky will drag me off with the sheep crook if I go massively over time.
Still 15 minutes left, Rob, but we can overrun if everyone's happy with that.
Oh, right, okay, right. Well, that's about right, actually. So that was a bit about climate change. And now we'll go on to the effect of the hydraulic effect of ditches in peatlands. So this picture here was, I'm somewhat ashamed that I was responsible for this. It was actually a research project. So this isn't designated peatland, or it turned out it was really nice blanket bog, but it wasn't designated as SSSI. And we did a research project for CCW at the time, where we got funding to instrument the blanket bog quite heavily, and then we got a local contractor to dig this ditch through the bog, and then we put some water control structure on it, so we could vary the level of the water in the bog and see what effect that had on the water tables to either side of the ditch. And this is a picture of a ditch in the Nant-Franken Valley in Snowdonia, but it's just downstream of Llyn. So the direct effect of functioning ditch is to lower water levels along its course. And the purpose of putting a ditch into a peatland is to maintain a lower water table in the ground adjacent to the ditch, with a view to making the ground fit for other uses. So, you know, grazing or arable farming. So here we've got our black line here is our ground surface, and our blue line is our water table. So that's our very perhaps excessively simplistic peatland, but there we are. So there's our peatland with our ground surface and our water table, and our Mr. Landowner, Mr. Farmer, comes along and he digs a ditch in the peatland. So immediately, if his ditch is functioning properly, he lowers the water table along the line of the ditch, and this level in the ditch is effectively expression of the water table locally. So he's just done that, literally just done it. And what are the effects of that? Well, the first effect is that you get drawdown to either side of the ditch. So compared to the water table when he first dug it, the water seeps into the ditch and gets taken away. Then you get drawdown of the water table to either side of the ditch. You'll also usually get, so you've got that zone of water table drawdown, which is marked by the red line. And what you usually get as well, interestingly, is a seepage trace. So if you go to a ditch, you'll often see a dry, this upper bit of the ditch, the wall of the ditch will be dry, and then the lower bit, you'll quite often see that it looks a lot wetter, and you might see some seepage coming out of the face of the ditch or the wall of the ditch. And that's called a seepage face. And the best time to see seepage faces is when it's really cold, because you can see where the seepage comes out of the seepage face. It immediately freezes. So you can see here that this is a photo taken on the peatland, and you know the seepage face can be seen because you've got a nice covering of ice over the side of the ditch, so you can tell that there's seepage out of that almost continuously. So that's the direct, so that's what we call in hydrological terms, that's what we call direct drawdown. So that's the zone of direct water table drawdown, and that's that's the first effect. And you'll see that that's on a flat peatland, a completely flat peatland. So there's a second effect, and this is a separate effect, but the two effects are additive. The second effect is intersection of downslope flow. So here we've got our simplistic peatland, but this time it's on a slight slope. So we've got the ground surface and the water table again, and we can see that we've got a certain amount of groundwater flow in the peat down slope in response to the hydraulic gradient we've got on the water table. So that's our natural situation. And then again, Mr. Farmer comes along and digs a contour parallel or a contour oblique ditch across our peatland to take water away. So what we find then is that the water that's flowing down in the peat is intercepted by this ditch. So that's why I'm saying it's intersection of downslope flow. So the water that's flowing down from the top is intercepted by the ditch and taken away, and we've got a certain amount. This is the direct drawdown of the ditch, means that we've got a certain amount of flow back up slope into the ditch. But the effect, what's the effect on the amount of water which is flowing down slope of the ditch? Well, it's actually, and this is portrayed by the smallness or the relative size of the arrows there. You can see that immediately downslope of that contour oblique ditch, you've got a lot less water flow in the peat. And the fact that you've got a lot less water flow in the peat means that you've got the water table is lower. So just from an intersection point of view, the function of the ditch intercepting the water flow in the peat, you've got lower water tables downslope of the ditch. And as I say, the direct drawdown and the interception functions of ditches are actually additive. So those two things work together to lower water tables in the ditch. So those are the two things that I'm going to talk about. So we briefly talked about climate change, and we've briefly talked about ditches. I think this will be available either as a presentation or as a video file. This is going back to, you saw this diagram earlier on, and these are all the water supply, water loss and water retention functions in our peatlands. So this is our thinking model, and for each of those here, I've put a little call out saying the many and various ways that humans have thought of for messing up the hydrology of peatlands. So for each of those functional elements in our sort of how does our peatland work, then these little bubbles show or explain to you how humans have managed to mess those up. So I'm not going to go through that at all, and I've only put that in there for reference, but you can see there's quite a lot of information in those bubbles. So it's, you know, just from that you can see that we've thought of quite a few ways to mess peatlands up. So we'll move on. And so how are we trying to fix the mess? Well, blocking ditches is one thing that we're doing. So on the left-hand side there, we've got recycled plastic micropiling. That's on Hirwine Bog, on the Heads of the Valleys Road, near to, I suppose, Penderyn is the best reference point now, where they make the Welsh whisky. This is Waun Fach, which is on the Black Mountains, near to, well, between Hay and Wye and Crickhowell, I suppose. So right on top of the Black Mountains, this is blocking ditches using timber dams. And this is a peat dam, so just piling peat back into the ditch. So you've got, this is the upside of the ditch, and this is the downside of the ditch down here. So this is just a peat dam which is put in the ditch, and this is in Scotland. It's just photographed during a visit to Scotland just before Christmas last year. So those are the main types of blockages of ditches: plastic piling, timber, and peat. So this raises the water. This raises the water level in the ditch, and it raises, you know, it reverses some of those effects that we were looking at in the previous slides. So it raises water tables to either side of the ditches. But when there's been a few studies, and when you do this, you find that you don't raise the water table within the peatland to the original height immediately. Anyway, it might, you know, things might develop, and you might retain a more natural situation. But in general, you attain a sort of semi-natural hydrology within the bogs, where the water table isn't quite as high and is more prone to falling during dry periods. So I won't go through this too much because it's a bit too detailed, but the first photograph you saw there on the left-hand side was in Hirwine Bog, and you can see the pink line there was actually in a ditch. The graduations here are every 20 centimetres on the y-axis, and the pink line was actually the water level in the ditch. So we installed the plastic sheet piling in the ditch at this point, and the water level in the ditch immediately went up about 30 centimetres. And if you look more closely, you can see, you can inspect this on your own once you've got this presentation or whatever. You can see that some of the water levels actually in the peatland to either side of the ditch went up as well. So that was fairly successful. And another technique which has got a lot of favour at the minute is low elevation trench, what's called low elevation trench bunding. So what you find is the long-term drying and oxidation of peat has often raised the permeability, or generally raised the permeability of peat, so on a much wider scale. So it's not just the ditches, it's that we were talking about, that kind of existential property of peat earlier on, being that it's low permeability, it's got a low hydraulic conductivity. And quite often when peatlands have been dried over a long period of time, that natural low permeability has been lost, and the permeability of the peat has been raised a little. It means that the water tables, because of that higher permeability, the water tables don't reside at as high a level as they should. So, and that means that more extent, if you're going to restore the peatland, it means that more extensive treatment is required to raise the water table over the whole peatland. And one technique that's been employed for this is called low elevation, it's a bit of a mouthful, but low elevation contour parallel trench bunding, which was originally developed, I think, in the UK by, on the South Sawl mosses by a guy called Alistair Brock. And as I say, it's currently been used quite extensively in the UK. So again, you can study this at your leisure if you want to, once you get the presentation. The key thing here is this is the original peat surface that I'm tracing across here, and the green peat is the peat which has been oxidised over the long term, so that's quite high permeability. The key to trench bunding is that we dig a trench, so these brown walls here effectively, we've dug a trench there and we've refilled that trench with this low permeability with peat that we're taking out of this borrow pit up gradient of the trench. So we move this peat in here, we get a digger and we dig a trench and we put this peat in here. So you can see the overall effect of that technique. And these as you see in the name, contour parallel, the bunds are contour parallel. So the effect of this is to effectively put underground dams within the peatland, which holds up the water table. So you can see this dashed line was the previous water table in the peatland, and once we've done our low elevation contour bunding, we're maintaining a much higher water table in the peatland, because basically we've increased the hydraulic resistance for water flowing in the peat from upstream here or up gradient here and to down gradient to the left hand side of the slide. So that's the sort of theory behind these low elevation trench bunds. And this is a picture from Borth Bog, which is the most these things are quite difficult to illustrate sometimes. These have just been done at the time. You can see there's a nice trench bund here, so this would go down about a metre into the ground. You can see the borrow pits behind it. So this is a relatively low permeability wall of peat, and it's providing resistance. So if we measured the water, you measured the elevation of the water here, it would almost certainly be much higher than the elevation of the water table downstream of the bund. So we're holding, the effect is to hold water on the peatland for longer. So that's a technique that's been used quite extensively, and I'm sure that I know Hayley's listening, or well, maybe she's might have bored her to tears by now, she's gone away, but I know that Hayley's used this technique in the South Wales upland peatlands. So some take homes, that's very American, isn't it? Sorry. So water and peatlands are fundamentally linked. We've been through that. Spatial distribution of peatlands in the UK is strongly and positively correlated with the spatial distribution of effective rainfall. Brackets, peat happens where it's wet. Surprise, surprise. The nature of peatlands tends to retard water runoff and outward seepage. So they're flat and peat is poorly permeable. That means the peatlands retain water for longer and have got increasing saturation. So we've found many and various ways of messing up the hydrology of peatlands, although interestingly, it's not, quite often it's not been successful. There's a lot of natural sites where there's lots of drainage ditches running all the way through natural peatlands, and they're not used for anything that's profitable in agricultural terms. So it proves to me that in a lot of cases, peatlands are actually quite difficult to drain, economically anyway. And peatland hydrological restoration is difficult, but we are, I think, gradually developing and refining effective techniques to restore it and bring it back into favourable condition. But it's not, it's not that easy, and we're still learning how to do it. And I think that's it. Yeah, there we are. That's Wedi near Cael, a lovely raised bog surrounded by limestone cliffs, which everybody should visit because it's very pretty. So yeah, thank you. Hopefully some of you are still listening at least, and any questions are welcome.
Thank you, Rob. That was fascinating. So you're being far too hard on yourself. I'm sure everyone agrees. No, genuinely, I'm not just saying it because I'm the host. I found that amazing.
Hi, Rob. Within the Mardy area, we have a horrendous problem with off-road activity, largely bikes, but also a large number of 4x4s, which cause absolutely horrific damage to the point that farm cattle get caught in the bog areas, which have been troughed out by the off-road activity, some of them to depths to 3 to 4 foot deep. It was quite interesting where you mentioned that the dikes that cause damage to the peatlands. Has any research been done to actually offer mitigation for local authorities, NRW, and all the relevant bodies to work together to, we know it's an illegal activity, but very little is done, particularly in this area, to actively prevent the off-roading. And people are travelling in from Manchester and Birmingham to actually violate the mountaintops here. Are you aware, or have you done any research with that proves the damage that the off-roaders actually cause in peatland?
Oh gosh, yeah. I mean, I'm afraid it's going to be a counsel of despair. The main experience that I've got of this is working on Weinbach with Jonathan Sawl on the Black Mountains, and this is something that I've got some more stuff that we can have a look at if we've got time or anybody's interested. But the main thing that I would say in relation to those aspects is that peatlands are incredibly fragile ecosystems in terms of their hydrology and their form, if you like. And what you find on the Black Mountains is, I don't think this is any degree of exaggeration. The problem up there is generally motorbikes, so similar to what some aspects of your problem. And what you find is that even one pass of a motorbike, the nature of peatlands is that you get this negative feedback loop in terms of the micro geomorphology and the micro kind of hydrogeomorphology, if I'm not putting too many terms together there. So you get one pass of a motorbike, and if that one pass of a motorbike causes any kind of line in the peat, in the surface of the peat, you get, and that results in some concentration of runoff, then that concentration of runoff will start to erode, and the erosion will lower the base of that line, and lowering of the base of the line means that you get drawdown to either side of it, and you get more concentration of runoff. Yeah. And the more concentration of runoff you get, the more erosion you get. And quite quickly you can see that from a relatively innocuous start with just one pass of a motorbike, within a certain amount of time you can end up with like a 4 metre deep gully in the peatland. So as I say, it's a bit of a counsel of despair, because when the system is that fragile, it's really difficult. And the only, I don't know how you deal with it, to be honest, because the only way of stopping that is to completely stop these people coming on. I mean, law enforcement, I'm glad to say, is beyond my area of expertise, but yeah, it's really difficult, and really fragile and sensitive ecosystems which could get ruined really easily. So I'm sorry to say that. I wish I could be a bit more positive, but I mean, you know, we've made progress with damming ditches and stuff but you know, depending on where you are, if you start putting stuff like plastic sheet piles or timber dams into peatlands, quite often people, you know, enjoy vandalising those too, I guess. So I don't know. Sorry.
Oh, are there any actual papers that you've actually been part of that could actually be presented to the local authority here, and then I was able to say, look, this is categorical evidence of off-road damaging? Because when I've complained over the past few years, and the last 2 years the problem has intensified. Over the last, during lockdown, we've now got off-roaders here 7 days a week. So it's gone from 2 days a week, primarily one evening a weekend, and always a Sunday flat out, to 7 days a week. And they're tearing up so much ground. I specialise in coal spoil. So my coal spoil is she's surrounded by upland heath peatland, and the water table on my coal spoil changed last October, and she's now flooding out an area of self-draining coal spoil which has never held water, never had water retention, and now she's holding water. And when I say holding, 4 foot deep, 5 foot deep. So I'm still waiting for an ecology team to come back and say, yeah, you know, there's a problem. And instead of going, oh yeah, but it's off-roaders then, my hands tied. And the off-roaders say we do no damage. And the farmers up in arms, they've had meetings with the National Farmers Union due to livestock being trapped up here, to the point that, you know, exhausted. They've not yet died. They've caught them in time. But like you said, that some of these ditches are so deep that cattle are getting caught in them and can't get out.
Yeah, I mean, I would say that, I mean, I've got nothing that I can give you immediately, but I'd say that getting in touch with Jonathan Sawl would be useful, because he's got a lot of evidence up there. I did a bit of work on the Monk's Trod, which is an old, an ancient pathway between Strata, Florida and Abbeycombe here in the Eland Valley. And they've got very similar problems with motorbike access up there. So there's some access people in Powys County Council, and also mainly the Powys County Council people. It might be useful for you to get in touch with those. So if you drop me an email, I'll look back in my emails and find you a contact, and you can email them as well, because they're going through exactly the same issues as you are.
Oh, fantastic. That'd be good. Great. Thank you, Rob.
Okay, we got a couple more. A comment from Emma Scotney saying, thank you, Rob. Very interesting. I'm based down here in southwest UK, and we have started to do a lot of restoration of peatlands via timber filling of ditches for habitat restoration, water resilience and quality. You've given her lots of things to think about in terms of our long-term management considering climate change. There you go. And next question. It looks like water level restoration is quite quick. How long does it take to get sphagnum colonization after ditch blocking, etc.?
Well, I mean, the first thing to say is I'd probably ask Joey or Mike about that rather than me. But in my experience, the sphagnum starts to develop actually within the ditches quite quickly, because you've got very saturated conditions in there, and you get the species that develop underwater, and hopefully it's useful to say at this point that I'm very keen on saying that the peatlands that we're looking at have generally developed over since the Holocene started, so maybe technically about 12,000 years, and we've managed to mess them up. So they've been developing over that period of time, and we've managed to mess them up relatively quickly. And I think we're we have difficulty with the sort of administrative and management horizons, time horizons that we have to work with. And I think rather than saying, okay, we're going to restore that peatland and we're going to be expecting it to be completely functional and favourable, like the day after we've restored it or tried to restore it, I think that's generally the wrong way to look at it. I think what we should be saying is, okay, we're going to restore it, or we're going to try and restore it. What we're looking for is evidence that it's going in the right direction, that we've made a sufficient difference, so that the peatland is going to develop in a positive direction, rather than, and that might happen. That might happen over the next 100 years, or it might happen over the next kind of 500 years. But that's the criterion that we should work on, rather than letting managers and the various bean counters say, "Oh, you've not been successful because A, B, and C hasn't happened." We need to be quite proactive in saying, we're just kind of reversing the trend here, and we've got it into a positive into a positive situation. So, I mean, I'm waffling here a bit because I don't know. I mean, yeah, I'd ask Joey. I know that quite a lot of the time, I've seen people seeding sphagnum as well, to kind of hasten the process to get sphagnum developing. But yeah, I'd defer to ecologists rather than me trying to wing it on ecology.
Okay, thank you. Next one is kind of an ecology question too. What's your view on the effectiveness of planting sphagnum plugs?
Yeah, Joey, Mike.
We do have Mike and Joey here, I believe, today. I don't know if they want to comment. Otherwise, I can provide contact details for them in the chat.
Yeah, I am here. I was just typing out a response to that last question with regards to how fast sphagnum colonises the areas. I use the example of Borth Bog because I was there last summer in some of the same areas that Rob had worked on. And I looked at the recolonisation of sphagnum in those areas, and what I found was immediately after kind of in that period of 2 to 3 months, you got very little recolonisation. Then when you look at some that are kind of 1 year, 2 years old, you get some recolonisation, but they're species that are either present right there in the area that have been spread during construction, or they're ones that seed themselves in areas that are kind of more disturbed. And then when you look at the ones that were done maybe 10 years ago, which tends to be more plastic piling on Borth Bog in the central areas, you get a carpet of kind of nicer species like papillosum, which are kind of actively peat forming. So yeah, I hope that answers the question.
Thank you, Joey. Okay, that's all of our questions. So unless anyone has one they want to quickly sneak in now, feel free to unmute yourself so we can all thank Rob for a really fascinating talk. Thank you, Rob.
Thanks a lot.
Cheers, Rob.
Thanks,
Thank you,
Rob,
that was
great.
brilliant. Thank you, Rob.
Thank you.
Thank you.